Differentiation, if you're not already familiar, is a topic wherein we can work out the gradient at any given specific point on a curve. Now, this video here isn't going to be going in depth into the basics behind the methodology of differentiation or any of really the more complex rules you'll go onto as we try to differentiate larger expressions. So if you're looking for those, you can find other videos among our collection. Here, though, what we're going to be looking at is more the proof behind that methodology of differentiation. Why is it that if we take the coefficient times the power and then lower the power by 1, why is that the expression that will then get us the gradient at that point? This is what you may have to show in a question. This is what is known as differentiation by first principles. Now, this coordinate down here, therefore, we could just label as x, f, x, whatever the starting coordinates are going to be. Then, to get the coordinates of this other point, such that we have a difference in x and difference in y, what we can do is set up this kind of triangle. So specifically set up a dotted line between the x coordinates and then in the y as well. And what we'll do is I'll label this base, this difference in the x, h. Therefore, this x coordinate up here is going to be x plus h, because starting x, now we've gone h to the right. The y coordinate, therefore, is then the f of x plus h. By doing the y coordinates in terms of fx, this allows us to take into account this specific h value when describing that coordinate. If we were just doing it as an amount of y, we don't know how this rise in the y-axis will compare to the going across in the x-axis. This is the only way we can ensure we have the exact same value having an effect. Now that we have these, therefore, if we were just to draw a straight line between these 2 points, because that's what this will be working out, we could have the gradient of that line, but as we can see, that doesn't match the curve. That's not going to be the same gradient. So what we can do is we can bring this second point closer. Let's say we brought it here. This then will have a new triangle going across that we can also label h. And if we then got the difference between those points, or so still the same starting point, but now this second one here, still this straight line doesn't match the curve. But as we can see, it's closer. To make it even closer again, we'll just draw this point even further left. So we have yet another triangle where this is now a new h value. Drawing a line between the dots here. Once again, we're getting closer and closer to the curve, even though we're not meeting it. Therefore, what we can say is that as h tends towards 0, as h limits towards 0, the dy over dx, or in this case, the f dash for the differential of the function, this is going to be closer to what the true gradient would be. The actual implications of this h limiting towards 0 we're going to come back to later on, but right now, regardless of what h value we've picked, let's plug them into this difference in y for difference in x. So y2 is going to be this f of x plus h, and from that you'll minus your y1, which would just be the f of x. And dividing this, your x2 is the x plus h, and your x1 is just the x. On the bottom, though, now, in the denominator, we have a plus x and a minus x. They're going to cancel with each other, regardless of what x is, leaving us with just h on the bottom. Therefore, the formula we are going to use when working out our differential by first principles is the f of x plus h, where h is just going to be some generic value, minus the regular f of x all over h, and then in this h is limiting towards 0. Now that we have this formula, we can finally apply it to some equations that we're trying to differentiate or just find the gradients of. Let's say to start off with that we had the f of x being 2x, okay, so the equivalent of y equals 2x. The f of x plus h, therefore, is going to be 2 lots of x plus h. You replace the x with x plus h. If the x was being times by 2 before, now the entire x plus h, or whatever's in the bracket, is now being times by 2, as you would do with functions in general. What's in the bracket replaces the general x. Taking these and putting them into this formula, therefore, you end up with 2 of x plus h minus 2x over h. Expanding this here, that will be 2x plus 2h minus 2x over h. This term here, the 2x, is going to minus with the 2x at the end to cancel. In general, in first principles, the thing on the far left should cancel with the thing on the far right, so if it doesn't, just double check that you've done the first step correctly. This leaves us with 2h over h, which is just going to be the same as 2. And if you just want to double check with your usual differentiation method, you'd think of this as a power of 1. So coefficient times power, so 2 times 1 is 2. Drop the power by 1, it drops to a 0. X to the power of 0, or anything to the power of 0, is 1. So 2 times 1 is 2. This is indeed the gradient. And just another example, if we'd had the f of x was instead x cubed, what this becomes is the f of x plus h is x plus h cubed. So putting it in the formula, you have x plus h cubed minus x cubed over h. Now we are going to have to expand this. If you're not sure how a cubic bracket is going to expand, which is fine, you'll do it first as like a square bracket, so the x plus h squared, and then times that by x plus h afterwards. So squaring the bracket first, that's going to be x squared plus 2hx plus h squared. That's being times by x plus h minus x cubed over h. Now timesing these brackets out, you end up with x cubed plus hx squared plus 2hx squared plus 2h squared x plus x h squared plus h cubed. And then minus the x cubed here, all over h. Bringing together the like terms, x cubed minus x cubed is just going to disappear. Then hx squared plus 2hx squared is going to be 3hx squared. And then 2h squared x plus, well, the same as h squared x is going to give us 3h squared x, and then plus h cubed afterwards. This then still over h. Dividing through by h, you end up with 3x squared plus 3hx plus h squared. Now at this stage, we still have some h's left that we're not expecting to be there because we have no value for h. This is just a general term. And this is where that h limiting towards 0 comes in. Because we're saying throughout all of this, h trying to tend closer and closer and closer to 0. So essentially it's going to become negligible. It makes no difference to the overall value. Therefore, any term that still has h in it might as well just disappear. It may as well not be there. Thus leaving us with just 3x squared, which is what you would expect to get from this x cubed being differentiated. Coefficient of 1 times the power of 3 is 3. Lower the power by 1, you get a power of 2. So if you have any h's left over after you've done all of this, just get any term that contains the h to disappear, because it's like timesing by something that's basically 0. So if we're clear on what we're doing here, how we're taking our original expression, adding an h to the x value to get a new expression, taking that new one minus the old over h, then expanding and simplifying. If we are therefore okay with the methods behind first principles, let's just see how you might get along with a question of your own. I'll just leave this up here so you can compare if you so wish, but in general, if you were to instead have that the f of x x equals the 4x squared plus x minus 1. How could you show the differentiation of that by first principles? Yes, you do now have multiple terms, but you will still be considering the expression in the exact same way. So, pause the video, have a go for yourself, and then press play again when you're ready to compare. Alright, so first of all, we should get our expression for the f of x plus h. In this case, we'll replace every x with the x plus h, so it's 4, and then that in brackets, then plus x plus h, and then minus 1 at the end. So, putting this now into our larger formula. Actually, I'll expand this right now first of all. So you would have 4 lots of x squared plus 2hx plus h squared. And obviously that's going to be plus x plus h minus 1. And then minus all of the original 4x squared plus x minus 1. This being all over h. Expanding out these brackets here, you end up with 4x squared plus 8hx plus 4h squared. And again, the plus the x plus the h minus 1. And then here is a minus 4x squared minus x, but then minus 1 is a plus 1 all over h. Considering your like terms, you have your 4x squared minus your 4x squared, so they're going to cancel. And you're going to have a plus x and a minus x, so they're going to disappear. And then here, you're going to have a minus 1 plus 1. So they're also going to disappear. So as you would usually expect, the entirety of your original fx cancels away. So this has left us with 8hx plus 4h squared plus h. So dividing everything through here by h, you're left with 8x plus 4h plus 1. And for this, again, because h is limiting towards 0, this term here is going to disappear, leaving you with the differential of fx being 8x plus 1. As we would expect, we're doing the 4 times 2, which is 8, lower the power by 1, 1, and then here a single x will differentiate to that 1. If we're good with that, let's just move on to one further question. Now, within the differentiation, not only are you going to be differentiating general x terms, but as you go forwards, you'll end up also differentiating trigonomic functions. So, given that x is measured in radians, prove from first principles that the derivative of sine x is cos x. You may assume that the formula for sine a plus or minus b, and that as h limits towards 0, sine h over h will tend towards 1, and cos h minus 1 over h will tend towards 0. Now, if you're not familiar with any radians, or how to differentiate sine and cos functions, or what this formula here is, the addition formula, radians will be primarily discussed in the solving for angles within a range in the trigonometry section, as well as just cropping up in a few other videos here and there. The differentiation of sine and cos is going to come under the different rules for differentiation. And then this here is part of your trigonomic identities, as I say, the addition formulae. As always, I'll just be going over them here briefly anyway, just in explaining the working though. The question confirms for us that we're going to be working with first principles, so we need to set up an fx and an fx plus h. So fx is going to be that sine of x, and then your f of x plus h is going to be the sine of x plus h, again, all within the brackets of the function. As we put this then into our formula, we'll end up with a derivative of fx being this sine x plus h minus the sine of x all over h. Now, using the addition formula here, we've got two things added together inside of a sine function. We can say that that's going to be the same as sine x cos h plus cos x sine h, obviously still minus the sine x, and then this here, again still over h. At this stage, we may wish to split this big fraction up a little. Maybe not into all three terms, like so the sine x cos h over h, and the cos x sine h over h, and the minus sine over h. We'll just group together the cos x term on its own, but then group together the sine x terms, because as we can see here, if we can get these as a single function over h, then we can replace these with the values of 1 and 0 respectively. So, looking at the cos x, because that's just going to be the single term, you'll have cos x sine h over h, and then that has added to it the sine x cos h minus sine x. At this point, we can actually break them down even further. If we were to factorize out each of the x terms from each of the fractions, leaving you with fractions just in terms of h. So you end up with this cos x factorized out of your sine h over h, and this is added to sine x factorized out of cos h, and then if you took out sine x, that just leaves us as minus 1 up here over h. Now we know from the above that sine h over h is the same as 1, so that's just the same as cos x times by 1. And here, the cos h minus 1 over h is the same as 0. It tends towards 0 as h gets smaller and smaller, which is what would be happening in these cases, as has been above. So cos x times 1 is just going to be cos x, and sine x times 0 is going to disappear. So you end up with your differential just being cos x as you wanted. In general, if you were looking to work out the gradient between 2 points, you would use the equation y2 minus y1 over x2 minus x1. So the difference in the y's over the differences in the x's. If for this we were trying to apply this to this curve, we just say we pick a point here and a point here, and just for clarity, let's label this line y equals fx, because later on we'll see that it's going to be better for us to represent the y coordinates in terms of an fx rather than a y. Again, that'll hopefully become clear in a second.